Okay. So now we have to start looking at the problem in a much more practical way. Okay. So now we understood the limits of what we can do. Okay. Where we eventually are going to get. And please don't get me wrong. I am not saying that we cannot come up with answers for these things. The problem is, what I'm saying is that you cannot come up with answers if you think that you can plow through first principles and brute force arrive to the answer. You will be stopped at some point. Okay, we don't have the capacity to start from the very basic and bring all the way to the answer. We have to circumvent the problem at some point. We have to feed the problem with some empirical data or something until we create an answer that is valid. Is that okay? So, I was talking about yesterday about the candle, and there you can see my wick that is bent and how it's touching, you know, the flame and is consuming itself, and that's the way in which you maintain a flame that is actually not sooty. In other words, it's a closed-tip flame where you have full consumption of the soot. So this candle will have a soot yield of 0. Is that okay? So there will be no production of soot emerging from the top of the candle. Everything is oxidized, so effectively your balance between production and oxidation leads to 0. Okay? The moment that you get enough strain and the flame breaks, then you're going to get soot production. Now, in turbulent flames, that's going to happen everywhere. So if I look at my wrinkle flame, in reality, it's not a continuous wrinkle flame, but there's going to be points of great stretch where effectively you're creating so much strain on the flame that the flame is going to quench. Okay? So you get what people call the flamelets. And the flamelets are just bits and pieces of flames. And you get points where soot is going to escape. Okay, that's very common from highly strained turbulent flames. Now, fire flames are really not highly strained, but nevertheless, they do have locations where that happens. Now, normally that's a function of the diameter. If you make the diameter very small, you can actually burn everything because the air and the fuel more or less manage to meet in an appropriate way. The moment you start making the fire bigger, then the air cannot be entrained correctly, and you're going to get pockets where effectively you have a lot of strain because the oxygen cannot get there. Okay? And there you get quenching, and there you get loss of smoke coming in. So normally at the core of a flame, you will get a lot of soot being produced in that place, and you will get less being produced at the edges of the flame. So, okay? So, here's a candle, and again, you know, as you can see, it's a stationary process by which effectively you have the fuel being produced in the wick, the fuel migrates, oxygen is being entrained, but in this particular case, because the source of the fuel is a point, and the flame is actually very small, then effectively you do not get the same instabilities that you will get in a larger plane where you actually have a situation like what I was describing there. So you will still get some fluctuations, particularly at the top when the velocities increase, but generally, particularly the bottom of a candle will be fairly stable, and there will be no fluctuations at that point. It is not an unstable situation. Now, the problem is that once you get into that candle, and then you get the problem of how that interacts with everything else, you know, within a compartment of relevance, okay? So this is a film by NIST. The objective of this film was trying to show the efficacy of sprinkler systems. Now, of course, they showed the perfect scenario, which would be a dormitory or a hotel room or a hospital room where sprinklers perform at their best. And this one will be a room with a sprinkler head. This one will be a room without a sprinkler head. You've ignited a waste paper basket, and effectively you let the two fires that are fairly identical, you know, progress. As you can see, the arrangements of both rooms are about the same. The flame starts growing, and eventually the sprinkler will be activated. So at the beginning, as you can see, is very, very well ventilated. So you can argue that the yield of soot of this particular flames is going to be very low because the average equivalence ratio is going to be very lean. Okay? So you get very little smoke being produced. You get a little bit of a haze, but that's mostly water vapor. And effectively what you get is almost a yield of 0 of soot, and the visibility is there. Temperatures are generally very low, and the fire continues to grow. So as the fire continues to grow, then it gets to a point where you start reducing the efficiency of combustion, and you get more incomplete combustion, and you start producing soot. In the one below, you can start seeing how, from this angle, you can see how it starts getting dark. So the soot that is being produced by the flame now is blocking the light, so there's an extinction coefficient, okay? And effectively, you start seeing less and less through it. You can see this happening at this angle also, and the fire continues to grow. At some point, the fire would have been big enough that the temperature of the smoke would be sufficient to activate the sprinkler system, and then the sprinkler head gets activated, water gets thrown to the fire, and in this particular case, the fire gets extinguished. Okay? So this one disappears, and this one continues to burn. Now, as it continues to burn, now we start changing the problem, because what we're doing is now we have a smoke layer that is hot, and that smoke layer is pushing itself downwards, reducing the area through which you can entrain the air. So now what you're doing is the flame is trying to entrain air, but the smoke layer is providing less and less area through which the air can be entrained. So given that you are entraining less and less, then the temperature of your smoke starts going higher and higher, but also the combustion becomes less and less and less complete. Okay, so as it becomes less complete, you get more soot, more obscuration, and the smoke layer continues to descend. So the process enters a system by which effectively at every stage you get less air entrainment, more incomplete combustion, higher temperatures of the smoke, and it becomes a vicious circle. Eventually, the temperature of the smoke is high enough that the radiative feedback is sufficient to ignite every material in the compartment, and that's what is labeled flashover. Okay? So you've exceeded the capacity of the materials to tolerate ignition, and then eventually everything ignites simultaneously. Okay? Now, at this point, you're reaching a condition in which now you don't have sufficient air. Okay? So in other words, what you have is an underventilated fire. So the door that is open doesn't allow the air, sufficient air to come in. You have too much fuel being produced. It's becoming extremely rich. Okay? Now at that point, if you put more air, and this is a discussion we were having yesterday, if you put more air at that point, you will get more combustion because you have more than enough fuel to burn. Earlier, at the beginning of the fire, if you put more air, nothing will happen because you have excess air coming in. Is that okay? So we've now made the transition. Now, it is more or less this point, where you effectively have a compartment at fairly high temperatures, and that compartment requires more oxygen to be able to burn. The glass is going to break eventually, and the moment the glass breaks, you get that extra supply of oxygen, and you will see how the combustion gets enhanced. Because of the richness of the fuel, you have very incomplete combustion. As you can see, you get all this black smoke coming out.
The reason all the black smoke is not ignited is that because
it's too cold.
Sorry?
It's probably still too cold.
Okay.
So as you can see, because it's so rich inside, the fuel is coming out. Now, and the combustion is happening on the outside where you actually can find more oxygen, to burn. So eventually all the glass panes will break, and you will see at each stage how the combustion starts becoming more and more and more intense. Okay, so the other glass is going to break pretty soon. And you can see at each stage that the glass starts breaking how the intensity keeps picking up. And you can also see how random the glass breakage is, no? Surprising that the middle pane is the one that... So this is a fire with the sprinkler. So of course the sprinkler stopped the fire very early. You only had some minor damage at this point, and then nothing actually happened. While the other case where the fire was allowed to continue to burn, you have basically almost total fuel consumption, and you reach burnout, and there's pretty much very little left. Okay? So, these are the stages of the fire, and this is a very common diagram that people use that basically shows you that you get your point of ignition at this point, and then the temperature remains very low for a very significant period of time, normally somewhere between 4 and 5 minutes for a compartment of that nature. And then eventually you start picking up the temperature until you reach a certain threshold, and that's where the smoke can produce sufficient radiation to ignite everything, and then you have this period of transition, which is flashover, and then you move in what is called the fully developed compartment fire. Okay? So what is the difference between these two stages? So in the first stage, the fire is relatively small, so it has sufficient capacity to entrain air and maintain itself under conditions where effectively the stoichiometry is on the lean side. Okay? You're going to send all the hot gases to the top, so you get an upper layer which is hot, and then some smoke that spills out of the openings. Okay? So effectively you're going to get air through a cold layer entering the fire. The fire produces the heat and the products of combustion. They go up and they accumulate it at the top layer. But in this stage, which is the two-zone stage, effectively your fire behaves as a well-ventilated fire. Okay, so it has more air than the one that it actually needs. Okay, now once the smoke layer has descended enough, then the area through which the air can be entrained is now so small that you have very little oxygen reaching the fire. You get a lot more incomplete combustion. Okay, you get very little mass of air entering in, so the smoke becomes hotter. Okay, and it starts effectively radiating downwards until eventually it ignites everything. At that point, you have so much fuel that you fill the compartment with unburned products of combustion, and all the exchange of oxygen happens at the opening. So it's mostly hydrostatic pressure, and effectively is sending smoke out and entraining air in, but it's all happening at the door. So the more openings you make, the more air you're going to have entering the compartment. So effectively, this is the ventilation limited regime, where you have excess fuel, is rich in nature, and effectively leads to a condition where if I increase the supply of air, the temperature will go higher. So if you look at a plot like this, normally what you have is that at some point you break the glass and the temperature increases from this level to this level. Now, whoever did this plot did something that is a little bit unrealistic, because unless you're closing the opening, which might be that you close a door, the temperature will not go down. Okay? So normally the sequence will be that you have one opening, then the next glass breaks, and then you get another one, and then the next one, and the temperature keeps going up. Is that okay? So when you look at the products of combustion, you can tell what is going on, because in this period of time, the oxygen concentration is almost as high as ambient. So you have about 21%, and it remains more or less constant for a certain period of time. But once you hit that threshold where the fire is growing rapidly, then immediately you start consuming all the oxygen, and when you get to flashover, the oxygen inside the compartment goes to zero. Okay? So effectively you're consuming all the oxygen in this section while you're consuming all the fuel in this section. This is fuel limited, this is ventilation limited. Is that clear? You know, one of the biggest misconceptions that people have is the concept that if I blow more air into a fire, then it becomes hotter. That only happens if you're in a ventilation limited condition. That from the perspective of life safety, that's meaningless, because if you're still there, I can guarantee you, you will be dead. So there is no question about it. So during the period where you're concerned about life safety is always going to be this particular period here. Is that okay? So you're in the earlier stages where basically I'm going to put all my measures to make sure that I get everybody out and I reduce the growth rate of the fire to guarantee that everybody's safe. So you will see your smoke alarms, you will see your sprinklers, everything is placed in this period here. Okay? Now, at the other end, what you are concerned is more about the structure, because this period here is going to last until you consume all the fuel. So this is going to be a much longer period than the 4 or 5 minutes of this period, and it's going to be at a much higher temperature. As you can see, it's about 700, 800 degrees at this point, where you actually can threaten the integrity of the structure. Okay? In this period here, you will have no threat to the structure because 1, the temperature is too low, and 2, the time is too short for the structure to heat up. Okay? Now, this created a very interesting situation because on the one hand, it allows us to simplify the problem. We are concerned on this fire if we're dealing with the structure, the underventilated condition, the fully developed fire, the fire that has already passed flashover, the post-flashover fire. So we have a very good design fire that enables me to address the structure. Okay? While I have a growing fire that is ventilated, in other words, fuel limited, okay, that is dominated by how the fire is getting bigger and bigger and bigger to do everything that has to do with life safety. So I have a design fire with a certain characteristics, with a certain conditions that allows me to establish how long do I have to get everybody out and how long do I have to activate all these protection systems. Now, in principle, the simplification is wonderful, no? Because it allows you to separate the two problems and address them in a completely independent way. Okay, structural problem, fully developed fire, life safety, growing fire. Is that okay? The unfortunate part is that by doing that, we also ended up separating two completely different disciplines. Because everything that deals with structures now is associated to that, and it belongs to the realm of, it would be fortunate if I said the civil engineers, but unfortunately, it lands with the architects. That's a different story. Okay? So it stays there, and that's a little bit precarious condition to be to give an architect a fully developed fire. But nevertheless, that's where it ends. Okay? So you create a professional divorce, because here you have everything that is associated to protection. So you have the fire protection engineers or the fire safety engineers all working diligently on life safety and addressing all these mechanisms of protection. But the moment that it flashes over, that's not their problem anymore. Okay? And as I say, unfortunately, the ball immediately lands on the architects who have absolutely no clue what they're doing, and then all of a sudden, nobody takes responsibility for structural behavior. In theory, if it would have landed on the structural engineers, we would all be very happy because they will be forced to learn about these things. And I know we have a couple of structural engineers in this room. But if you look at what, for example, if you take the North American codes and you take ASCE 7, the American Society for Civil Engineering, and the 7 code is the code that they use for design against hazards, okay? You know what it says? It says fire is such a rare event that a structural engineer shall not design for fire. Oh yes, it says it. I can show it to you later if you want. Okay? So what's the premise? We already accepted that the probability of a fire is 1. So how can we claim that it's such a rare event that we don't need to address it?
Maybe it's more expensive to, because we're talking about structures, not
Yes.
human beings. So it's more expensive to design for it than just let the building.
Not really.
Are you comfortable with that?
No. I mean, it's usual that your bathroom will cost more
Than the fireproofing.
the foundations. So you can have foundations for X amount of money, you can have triple X.
But
For
going
your
to the
bathroom
bathroom is not a
fittings.
rare event, right?
Are we dealing with professional socialization, the process of socialization of the engineers?
Yeah, absolutely.
Yeah, because, civil engineer makes lots of points in California taking the level 2 PE exam.
Yep.
Where he can protect against earthquakes.
Yep.
But as far as I know, nothing in the PE exam talks about fires.
Oh no, it's actually expressly excluded.
Yeah, okay.
Because, effectively the codes don't require you to address anything related to fire, and therefore the PE exam is not allowed to include any questions on fire.
So therefore,
Yep.
So then if it's not their responsibility, then somebody else should be allowed to make the call of whether something is up to standard or not.
Yeah, the architect.
well, some states do have a PE exam for fire protection.
Oh yes, but there's not a single question on structural behavior
Yeah, okay.
because we divorce the two disciplines
Okay, okay,
completely. We basically divorce them,
okay.
and it happened in 1928, so we are really stuck on it. Yeah.
Is this like a self-preservation measure made by civil engineers where they say this is just something we don't want to deal with, and so we just fudged it out of
To some extent it is, but it's not intentional. The way it happened, it was pretty straightforward. It happened so early on that the idea was that they couldn't understand how structures behave in fire. Okay, and because they couldn't understand it, they tried to find a mechanism by which they didn't have to deal with it. Okay, so the way in which they address that is basically, if you are very cynical, what a structural engineer or a civil engineer will say is that I have such a guarantee that the fire protection engineer will do his job properly, okay, that the fire will never get here. And even if it does, I'm going to insulate the structure to the yin-yang so it doesn't heat up and ever create a condition that could potentially fail. Okay, so that's the way they approach it. So effectively, they reduce, when they say that the fire is a rare event, they're not saying that the fire is a rare event. What they're saying is a fire that threatens a structure is a rare event. Okay, in other words, these guys are doing their job, so it will never get here. But even if it does, I put a very thick barrier of insulation that makes sure that the structure doesn't get to any temperature that is even close to create a problem for me. Okay? The problem is that that approach, one, hides all potential failures, and two, which is the most important one, for construction industry, is the cost is astronomical. Because blindness is very expensive because it requires very big safety factors. The way I look at factors of safety is they are a mechanism to compensate for your ignorance. So if you're absolutely ignorant, you need a massive safety factor. Okay, and that's the way we operate. Yeah.
So I think it's kind of that like early stage of like start of the civil engineering, they would say that okay, we don't know about this, so it's better to prevent this, right?
Yeah.
But what is holding this right now? What is holding this barrier right now?
That buildings are not falling down. So you know, right now, if you think about it, how many civil engineers do we produce every year in this country? Huh? Thousands and thousands, no? And they're all educated without a single heat transfer class. And this happens all over the world. So effectively, the change is at such a deep root that making this transition where you become, when you make it the responsibility of the civil engineer to design a building for fire, implies going all the way back to square one, redesigning the education of a civil engineer, then redesigning the whole definition of professional competency, and then effectively wait until that whole flow of incompetent people move away as you're trying to make them competent, shooting every architect that tries to still do the job, you know, which immediately creates a whole complicated situation, no? I mean, really, it's truly transformational. What we're asking is really a transformation of the discipline. Now, you will say, can it happen? Of course it can. And it actually has happened in the UK, for example, to some extent, you know, where people have begun that process. And of course, right now it still remains a specialty, but nevertheless, the transformation has begun. Yeah.
Do you not agree that it is perhaps on its way forwards in America? Like I was at SFE Europe with the board of directors meeting where they were sort of going on about how like they've established the core competencies, for example. So wouldn't you say that that's a step in the right direction? It's kind of addressing the fact that they need to.
Well, yeah. So effectively, both the American Society of Civil Engineers and SFPE have begun, you know, to move because there's a lot of economic pressure, you know, to do that. I mean, the fact that there is at least 2 civil engineers that I know in this room is a dramatic departure, you know, from what used to happen 10 years ago. So the process in the US has begun. You know, there's no question about it. Now, what SFPE is doing and what ASCE is doing, it is still in its infancy. So when SFPE did their core competencies, what they designed, if you look at the document, what they designed is an impossible engineer. So effectively, you have to be Leonardo da Vinci, you know, to be able to qualify, because all they did was they listed every competency that is associated to fire, and you're supposed to be proficient in every single one of them. And that's a bit problematic. So it's in its infancy. People are beginning to think about it, but they have not rationalized it to a point where it's actually applicable.
So would the solution lie in compartmentalizing it? Say, make a structural engineer who is equipped with a certain amount of skills, and then make the other one
The specialist.
Yeah.
Yeah, that was the solution in the UK. So basically what has happened in the UK is that now there are generations of specialists, you know, that are structural engineers that understand fire, that effectively are populating the discipline and serve as the anchor point, you know, for the discipline. Now, eventually that is going to have to expand, you know, because only 1 out of 1,000 buildings gets fire engineered when it comes to structures. And at some point that has to become a bigger thing. But yes, that was a process that was formed, that happened in the UK. So in the UK, you have a very well recognized structural fire engineering discipline. And it is a specialist discipline that is only in the hands of the very few. Okay, that doesn't happen here in the US yet. Okay, so there's no recognition for that discipline. Okay, so effectively that's where we are. So we separated the problem, and so we're going to try to look at the first problem, and then on Friday we're going to look at the second problem, and tomorrow I'll do the intermediate part, which is the material flammability. So here you have, that's a chimney. Okay, and with respect to the previous video, what have I changed? Yep.
The ventilation conditions.
Sorry?
The ventilation conditions.
Okay, so what is the major ventilation change that I made? Yeah, so basically you're evacuating the smoke, no? Is that okay? So by evacuating the smoke, I'm not allowing the smoke layer to descend. And the moment I don't allow the smoke layer to descend, the problem becomes stationary. Is that okay? You can see the fluctuations, okay? But it is a stationary problem when it comes to the fire itself. You know, all the fuel area is burning, so it cannot expand any further. And effectively, I'm not allowing this acceleration process that comes from the radiative feedback, you know, from the smoke. And I'm not allowing to move into a fuel-rich condition because I am not allowing the smoke layer to descend. Is that okay? So basically what you see this here is the zero interaction between the compartment and the fire. Yes, there's going to be some radiative feedback in here that is going to have some element, you know, that is going to alter the event, but eventually it'll reach a stationary condition, and it is the fact that I eliminated the smoke layer. Is that okay? Now, if I change now the problem and I don't allow the smoke to evacuate, so if you look at this video, at the beginning, I've opened completely the compartment, so you have your fire, and your fire basically is burning. The hot gases can go up, and they basically can leave the compartment. As the compartment heats up, then what I will do is block it in such a way, so I put a board in here to allow the smoke layer to build up. Here's the smoke layer, then the smoke layer starts radiating, and this is a little bit of wood, and you will see how this radiation eventually becomes intense enough that it actually can ignite the wood, and that's the moment where you get flashover. So I've turned a stationary problem into a transient problem that brings me into flashover just by allowing the smoke to accumulate. So I still have an area of entrainment because the opening is very large. But then eventually I get the flashover, this ignites. Now I'm producing so much fuel that effectively the entire compartment is burning, and all the exchange of air is happening at the opening. Smoke is being spilled out and air is coming in. Now there's so much fuel that the fuel cannot burn inside the compartment, so it's mostly burning on the outside of the compartment where you get oxygen. Is that okay? So you can see that change of allowing the smoke layer to be produced effectively is what determines the transition from one side to the other. So if you just make a diagram of this, basically this is what is happening. So you have your fuel in the bottom that is coming out, and then it's the air that is being entrained. The two of them produce smoke, and the smoke goes to the upper layer. So TU is the temperature of the upper layer, H is the height of the upper layer or the smoke layer. The smoke layer is descending with a certain velocity, and this is at ambient temperature, this is the smoke temperature, this is the upper layer temperature. This is the amount of air that is being pushed out because the smoke is still stuck, so it's not coming out. So effectively it's air coming out, air coming in to do conservation of mass. Is that okay? Very simple, straightforward concept. Now, this is our first order simplification. Okay? So what we have done is effectively rationalize the problem in a very unique form. Okay? And by doing so, I have induced certain fundamental simplifications to the problem. So effectively, one, I am not solving combustion anymore. Okay? Because if I create this framework, I have to prescribe the fire. Is that okay? Remember what we did yesterday with the alpha T squared? That's how I prescribe the fire. So I forget about combustion and I prescribe the fire, and the fire becomes a source of energy. Is that okay? Second, I'm going to eliminate the fluid mechanics. And effectively, all that this is going to be a transfer of energy and a transfer of mass. Okay? And whatever is happening in fluid mechanics, all I'm doing is saying all the mass that is being produced by the fire is going to land in the smoke layer. Is that okay? So I have no fluid mechanics and I have no combustion in the problem. Okay? So fire is prescribed, and the fluid mechanics is just dealt with as a mass. Is that clear? So from a practical perspective then, why would I do that? What is the objective of doing such a calculation? that is so simple. So what would be the purpose of doing such a thing? Okay, and why would I need to know that? Okay, and if that governs your flashover time, then how does that relate to people? Is that okay? So people have to be out of there a lot faster than that time. Yep.
People can't see, they shouldn't be allowed to see smoke in the first place.
Well, but this is a question you will decide. You know, I might decide that when 10% of the smoke layer, okay, has descended, keep in mind that I know that at the beginning there's so much air being entrained. Remember the video? Literally there was no smoke. There was a little fire in there, but there was no smoke. But if I do this type of analysis, even though the visibility might be still total, okay, you will still have a hot layer, because the moment that you're producing energy, you are producing mass, and you are creating in my framework a hot layer. That hot layer might not be gray as in my drawing, it might be transparent, okay, but it is still there, so I'm being conservative. Is that okay? So in principle, you're not seeing smoke, okay, but my model is telling you there is smoke, okay, because it's warm. Is that okay? But in principle, there's a very good objective. So the objective is purely to try to establish what is going to be the time for this smoke layer to descend to a position that me as an engineer, I deem represents the onset of hazard. Is that okay? And because it relates to the way in which people move, then clearly having a very coarse approximation is actually good enough. Is that clear? So I don't need to make it that precise. I can actually work this out in a way such that it becomes sufficient for the purpose. Is that clear? Okay? The purpose is to try to get a sense of how much time do I have available for people to get out. Okay? And as a function of that, I want to be able to calculate the descent of the smoke layer and make that my criteria. Whatever that criteria is going to be, that I will decide as an engineer, will be a function of the position of the smoke layer. Is that clear? And it could perfectly be the moment where I deem that the entrainment has been reduced sufficiently to start producing black smoke and affecting my visibility. Is that okay? Are we happy with that? So that's the concept of the zone model, you know, which divides the room into two well-defined zones, an upper layer, hot combustion products, a lower layer that is cold air, and that brings enormous simplifications, but it helps you understand a little bit the dynamics of the problem. Okay, so let me turn on the lights and work the concept of the zone model. Okay. So what am I going to do? Very straightforward. Here's my compartment. Here's my fire. And the fire is going to produce smoke. It's going to entrain air. And it's going to burn fuel. Is that okay? That smoke is going to accumulate in the upper layer, resulting in an increase of this distance, okay? You can define it as this distance, or you can define it as this distance, okay? Let's take the entrainment height and call this h of t. Is that okay? Are we all happy with that? Okay, so let's start then with the fire. And all I'm going to do is I'm going to forget about the fluid mechanics and effectively just do conservation of mass and conservation of energy. Is that clear? So what will be conservation of mass? The amount of air plus the amount of fuel gives me the amount of smoke. Ms is equal to Ma plus Mf. You see? That's conservation of. All happy? Sorry, mass.
Mass or energy?
My brain is going faster than my hand. Yes. Okay, so conservation of mass. So then I need conservation of energy, no? So that's the second one. So effectively, I have air coming in at ambient temperature. Okay, so my energy in is going to be MA CP T infinity. Is that okay? Are we happy with that? Fuel is going to come in originally at ambient temperature, has to be heated up, but the energy in is going to be MF CP T infinity. Happy with that? Whatever comes out is going to be M smoke CP T smoke. Okay? Some of you might be already cringing by the fact that I'm putting CP for everything, but let's just leave it there for the meantime. And of course, there will be the CP of the smoke at the temperature of the smoke. Yeah, all details. Okay? Yeah, it doesn't matter. We'll get there when we get there. Okay? So are we happy with that? So I can do energy in minus energy out? No? So what is energy in then? Energy in, the total, is going to be the energy in of the air. So it will be MA CP T infinity plus MF CP T infinity. Okay? Now, again, as I say, I'm going to use the same CP for everything. So it's just simply going to give me CP T infinity, and MA plus MF is MS. Are we happy with that? Hmm? Oh no, yeah, I have to do, so energy in minus energy out is equal to the heat release, no? So yes, of course, I have to put it in when I do my balance. Okay, so this is the energy that is coming in through the flow. Okay, so then I'm going to get the energy out. Okay, which is going to be MS CP TS. Okay, so energy in minus energy out. Sorry, energy out minus energy in. Energy out minus energy in has to be equal to the heat of combustion. Is that okay? So that will be the energy that is being released by the fire. Okay? I could represent it as MF multiplied by the heat of combustion, but I'll just put it as heat release rate. No problem with that? So, if I take the two of them, no? Yep. And now I can basically calculate the temperature of the smoke, and it's going to be T infinity plus Q divided by MS CP. Everybody happy with that? Yes.
Now the CP of the smoke and the air would be very close, right? But
Yeah.
what are we considering the fuel? Like if we have solid fuel, would that be much different? Like
Potentially.
orders of
I'm going to ignore it for the meantime. Okay. No, we'll talk about that. Okay. But it is correct. You know, I should have put the proper CPs. I should have not broken it. You know, sort of.
in the addition, because of the air and the smoke would probably be at the same order of magnitude. But if you have a solid, like solid burning or liquid, then that would be probably 1,000 times more. So we
No. That's not true. So CP doesn't change that much. Okay. So it does change, but it doesn't change 1,000 times. The density changes, but the CP normally will go between 700 and 1,400, so it's really not that big of a difference. Okay, but we'll get there. Let's not dwell on the details. Okay, yes, I agree with you that I should have put a different number here than the one I put in here. And of course, if we want to work the details out, that's exactly what we will do. Okay, I just want to get the concept right. So basically, we have conservation of mass and we have conservation of energy. Is that okay? Okay, so that works for the fire. Okay, so effectively all that is simple conservation of mass and simple conservation of energy for the region where you have the fire. Okay? Now I'm going to do exactly the same thing, but for the upper layer. Is that okay? So if I take the upper layer now, okay, what will be conservation of mass? So what is the mass into the upper layer? The mass of the smoke, no? So the smoke is going to the upper layer. So the mass in is the mass of the smoke. What is the mass out? It's accumulating. No? So unless I decided to put an extraction system, or it's going to be after it starts spilling through the door, but let's just not spill it for the meantime. Okay? Effectively, it's just accumulating, no? So in that case, the M out will be 0. Okay? And that is going to be the change of mass of the control volume. No? So it will be the change of mass of with respect to time of the control volume. Are we happy with that? Yep. So to be able to turn this mass into a volume, I have to multiply by the density, no? But that brings...
Divide by the density, I think.
Sorry, yes, divide by the density. So that brings the temperature of the upper layer, which I still don't have. Okay? Because that will define what the density of the upper layer is, because that's a function of the temperature of the upper layer. Are we comfortable with that?
With the ideal gas law.
Well, we'll get to the ideal gas law. We're going to have to use the ideal gas law. Is that clear? So, but we'll get to that point. So right now, I'm just going to put it as rho u. So this term here then becomes the derivative with respect to time of rho u times the volume, which is the area of the compartment, multiplied by the height. And the height will be h0 minus h of t. Okay? So what is A? A is the area of the ceiling. Okay? And this is h0, is the height of the compartment. So the smoke layer is h0 minus ht. Is that okay? At time equals 0, ht is h0. Okay, and as you move along, you get that. Everybody's okay with that? So then my conservation of mass then, it becomes the derivative with respect to time of rho u a h0 minus ht equals to ms. All happy? Yep. So if I do conservation of energy, then who's bringing energy in? Huh? Only the smoke, no? So energy in is going to be ms cp ts. Is that okay? Is there any energy out? No. Let's assume everything is adiabatic. Okay, so the smoke takes all the energy, no energy out. So that is equal to the change of energy of the control volume as a function of time. Everybody happy with that? What's the energy of the control volume? The mass of the control volume times the specific heat times the temperature of the upper layer. Okay? So I can change this, the derivative with respect to time, of the mass of the control volume times specific heat, temperature of the upper layer. Are we okay? Yep. So I can substitute the mass of the control volume by this, okay? And I get my conservation of energy. So I get d dt, mass of the control volume is rho u, A, H0 minus HT, okay? Times Cp times Tu is equal to ms Cp Ts. Conservation of energy. Okay? Final equation, as you mentioned, ideal gas law. I need the ideal gas law because that's the way I relate the density to the temperature, no? So can I represent the ideal gas law as saying rho over rho infinity is equal to T infinity over T? Is that okay? Is that the same as PV equals nRT? Yep. Constant pressure. There's no pressure increase in this kind of systems. So effectively, that's what it is. So if I increase the temperature, then the density goes down.
Wait, sir, we have constant pressure because we have a molten system.
Yes. So you consider everything to be incompressible. Okay? In the sense that if you increase the pressure, you create motion. Okay? You don't create a pressure increase. Okay?
Not incompressible.
Yes, low Mach number approximation. Okay? Are we all happy with that? You have to use the fancy terms, no? Because otherwise people think that you're just doing simple energy balances. So anyway, so here's all my equations. So how many unknowns do I have? Let's start. Do I know MA? No. First unknown. Do I know MF? No. Two unknowns. With these two, I will find this one, they're related, so I don't need to add a third. So then if I go here, do I know Q? Huh? You prescribe it. So how are we going to call Q? Let's call it Q equals alpha T squared. Is that okay? It's the growth period, and we did that yesterday. Are we happy with that? Yeah? So I know Q as a function of T. So Q is known. This is known. We know Cp. Okay, we know T infinity. Okay, so this equation gives me my third unknown. Okay? So the third unknown is Ts. Okay? But is related to all these other ones. So if I was to know Ms, then I will know the value of Ts. Is that okay? Now, if I go here, then in conservation of mass, I know H0, I know the area. Okay? This one is an unknown, that's number 4, that I know I'm going to get from a relationship here, okay? But it's still an unknown. Okay? So HT is an unknown, that's number 5. This one I already dealt with. So I have 5 unknowns. Okay? And then I go to conservation of energy. I already took care of this one I know Cp. And this is number 6, Tu. Are we happy? Okay? This is known. So I have 6 unknowns. If I take the ideal gas law, then this I will know, so I can relate temperatures to density, so I don't need to add another extra unknown because they're all there. Is that fine? So I have 6 unknowns, and I have 1 equation, 2 equations, 3 equations, 4 equations, 5 equations. Oops. How do you solve an indeterminate system with 5 equations and 6 unknowns?
Yes.
You have to guess one of them. No? Yeah. Okay, so it's 4:30, so let's take about 10 minutes so you can reflect on which one you're going to guess, and then I'll let you know.